Good morning. Yeah. Can you hear me? Can you hear me?
Yes.
Yeah.
Yes.
Sir, there is a lot of echo.
Yeah. It should be better. Is it better now? Sorry.
Still, there is a lot of echo, sir.
Yeah. Let me try now. Yeah. Is this better? Hello?
Yes, sir.
Yeah. Okay. So we are going to take, the class will go on for 1 hour till 10. And then I will give you one question, which is a slight modification of the 4 questions in the assignment. And then you will have enough time to write the answer and send it to the usual Gmail account. I will give you the instructions at that time. I noticed that in spite of the quiz, there are only 48 participants in the Zoom session. Well, so these quizzes are going to be pretty much every class will finish with a quiz. So, and these quizzes will count, even though each individual quiz will have a small weight, they will add up to something. So people have to be present and take the quiz if they want to get a reasonable grade. Very good. So let us start.
So in our
one second. Yeah. Who was this?
Sir Rohan.
Yeah.
Sir, in our server, we asked for people who are going to continue with semi, and only 43 people have reacted there. So,
Okay, that's interesting. Okay.
yeah.
Okay. And do you have feedback from the others?
Most are just going for JE, but like not all have responded is one issue, because we need to, because our faculty advisors told us to divide everyone into groups. So
yes.
that they can then do tutorials in groups.
Yeah. Okay, right. So that means that hopefully the people who are serious about continuing are here, and that is good. Very good. So we are dealing with matrices. So remember, so M cross N R is the space of, or at the moment I'll say it's a set of M cross N matrices with real entries. Okay. So that means a typical element of M cross M, this set is going to be an array A11, A12, A1N, AM1, AM2, AMN. There is a chat. Let me just see. Shakti Chauhan has written something. There are some people who aren't active on Discord. That is why they didn't react. What is Discord? Is Discord something like WhatsApp? Or is that the name of your group?
So Discord is like WhatsApp. Like Rohan said, pehle ki some people haven't reacted. We were using Discord for that. So that's what Shakti said.
So is Discord something like WhatsApp? Is it some other?
Yes,
yes,
sir.
sir.
Yes, sir.
Yeah, okay. I don't know about Discord. I know about Telegram, but I don't know about Discord. Okay, thank you. Well, hopefully we will settle down to a steady state, and also you guys will be back on campus, and we'll be able to do this face-to-face soon. So until then, let us try to do our best, everybody. Okay. So we know that you can make this into a vector space. This set M cross N R, it can be made into a real vector space. So if I have two M cross N matrices, A plus B is the matrix whose entries are A11 plus B11, A1n plus B1n, AM1 plus BM1, AMN plus BN, and so on. So you just add the entries at each place of the array. Okay. And if I have a scalar and a matrix A, the multiplication is just every entry gets multiplied by the real number, lambda. And this makes this set into a vector space. So now this has become promoted to a vector space. What was just a set has become a vector space, a real vector space, because the scalars are real numbers. More generally, if I look at a matrix with entries from complex numbers, then that becomes a complex vector space. If the matrix has rational entries, then that's a rational vector space over the rationals. And if it has entries from any field whatsoever, then the space of M cross N matrices with entries from that field becomes a vector space in this way. Okay. So now you can ask, what is this finite dimensional? And if so, what is the dimension? So exercise M cross N is a finite dimensional vector space with dimension equal to M times N. Okay, and so what does it? So we recall that vector space is finite dimensional if it's generated by finitely many vectors, in which case if you find a set of generating set that's also linearly independent, this number is independent of the set that you get, and such a set is called a basis, and the number of elements in the set is independent of which basis you take, and that is the dimension. So to show that M cross N R has dimension M cross N, all you have to do is to exhibit at one basis. So exhibit one basis with M cross N elements. And there's an obvious one. The basis elements are, you take all entries 0 except the ijth entry. So you fix an I and a row I and a column j, and you take the matrix with all entries 0 except the entry, the ijth entry, which is 1. And as I runs over 1 to M and J runs over 1 to N, you get M times N matrices, and these matrices are linearly independent and generate the space. So the dimension is M times N. So that you have to show why do they generate the space and why are they linearly independent. That's easy. Okay, but still, I put this as an exercise because this is something you should really check for yourself, just to get used to matrices, to get used to dimension, etc., in a simple situation. Okay, the 0 vector in this vector space is the 0 matrix, and the negative of a vector is the matrix whose each of those entries you reverse the sign of the first one. Yeah. So all this is very clear. So I will not spend time over this. There are particular kinds of matrices which are particularly important. So if m equal to if n equal to 1, so that means you have a matrix, the elements of m cross 1 have the shape A11, AM1, and the second index doesn't change from 1. There is no, the second index is just frozen at 1. So this is called a column vector.
Sir, I have a doubt in the notation.
Yes.
So why do you write R after m cross 1?
Yeah. So that's because
to denote it is a real vector space, is it?
Yeah. So if I so that is what I was speaking. I did not write it. So if I replace R by C or rationals, I get m cross n C, m cross n Q. So these are matrices with complex or rational entries, and they are respectively the m cross n C is a complex vector space, m cross n Q is a rational vector space, etc. More generally, if I have a field K, I can have m cross n K.
Yes, sir.
Okay. Yeah. So if the space of matrices where there is only one column, this is called a space of column vectors, and such matrices are called column vectors. So similarly, if m equal to 1, the elements of m 1 cross n R have the shape A11, A12, A1n, and these are called row vectors. So you better get used to it, even though the space m cross n is a vector space for any m and any n. The case when you have only one column or one row are special, and in those cases the elements are generally called not matrices but vectors, and you say row vectors or column vectors. This is for a reason that will become clear as we go along. So when you hear the word row vector, you should think of matrix with one row. When you hear the word column vector, you should think of a matrix with only one column. And a third class of matrices, which is important, are so-called square matrices. If m equal to n, so we have m cross m R is the space of square matrices. So in which case, to specify the size, I can just say of size m. Okay, but again, this is informally speaking. Okay. So these are, well, they are square. So A11, A1m, AMM, AMM. Okay. So these are square matrices, and they are particularly special for a whole lot of reasons, which we will come to. Again, you'll understand later. So these are special cases which are particularly important. Well, there are various operations you can do on matrices. A particular one is we have a linear map for every M cross N matrix A. You can define its transpose, which is usually I denoted A TR, A superscript TR, which is a N cross M matrix. Okay, so let me just be very clear. This is M cross N, and this is N cross M. Okay, so the number of rows and the number of columns are interchanged. Okay, so and how is this done? As follows. So you take this matrix A, A11, A1 M, A1N, AM1, AMN, and you just flip it around like this, A11, A1M, A1N, sorry, you see, AM1, AMN. So this is A transpose. So in other words, if I take A transpose, its ijth entry is by definition the jith entry of A. So this you do for every M cross N matrix. So that gives a map of sets okay, A goes to A transpose. You notice I am following my usual practice. I don't name a map unless I have to. If I already have a notation for what it does to an element of the first set, I use that notation instead. So I'm not, I could call this transpose. Okay. So then A transpose, the map transpose acting on the matrix A is what we have called ATR. But I don't give the map itself a name, meaning I don't give it a notation because, you know, unless I really have to, I prefer not to multiply names. Okay? But notation, this notation is important. So I prefer to use a notation for what it does to a given element. Okay. So now coming back to the transpose map from the space of M cross N matrices to from the set of M cross N matrices to the set of N cross M matrices. Now, these are not just sets. We have just seen that if I fix M and N, the set of M cross N matrices is a vector space. So on both sides of this map, I have not just sets, I have vector spaces. So it's natural to ask, is the transpose map a linear map? And of course it is. Well, what do you have to check? You have to check that A plus B transpose is A transpose plus B transpose. And you have to check that lambda times A transpose is lambda times A transpose. And these are easy to check. Okay. And the transpose of the zero vector is the zero vector, then transpose of the negative of a vector is of a matrix is the negative of the transpose matrix, blah, blah, blah. Okay. Now, finally, so this transpose has this property that if I do it twice, I get I get back to the original matrix. Okay, so if I take A, take its transpose, and take the transpose of that, I get back A. So in other words, the map from M cross N to N cross M to M cross N. So transpose, and the composite map is the, okay. So this is a fancy way of saying something very, very simple, which you see on the left, but I want you to get used to saying these fancy words because sometimes they stick in the memory better. Okay, so whatever you see in the red on the left corresponds to saying that the composition of transpose with the transpose is a certain map from M cross N to M cross N. What is that map? Are you guys there?
Yes, sir.
Identity map.
Identity map.
Identity map. So something extremely simple. We are just making it fancy because sometimes it's useful to do this. Sorry about this. Okay. Now I'm going the full hog with the fancy notation, blah, blah, blah. Okay, very good. So now the matrices get really powerful when you begin to multiply them. Okay, and so matrices of suitable sizes can be multiplied, and so here is the matrix multiplication. An incredibly powerful operation. So if B is L cross M and A is M cross N, so note that B has as many columns, as A has rows. So the key thing is the equality here. These numbers are the same. So if I take this, I can define a product which is a L cross N matrix. Well, I'm sure you've already seen this product. You know this product from high school. So if I call this C notation, then Cij is B I M A M J sum over n. No, I K. Sorry, M is fixed. K equal to 1 to n. So in other words, again, this is, you have to see this in many different ways. So if I take the product B11, B1M, BL1, BLM, and
And that should be B itself.
BB. I've changed it already. Thank you. M1, AMN, AM, N, AM1, AMN. Yeah. It's okay. AM1. No, sorry about this. A11, A1N. Yeah, have I got my indices correct? So then note that there are M columns here, and this has m rows. So this is equal to C11, C1n, CL1, CLN, where this given entry is got by taking the appropriate, okay, it is in front of you. I will not try to belabor this. Okay, so this is at the moment, this is, if you have not seen matrices before, this is quite a mysterious definition. Why do you define it like this? Why is it useful? So you just have to take it on faith that this is a useful operation. So let me just summarize this in abstract terms. What we have done is to give a map from the space of L cross M matrices, Cartesian product with the space of M cross N matrices, to the space of L cross N matrices. Okay. So take a pair, take an element of this Cartesian product, which is a pair BA, and that goes to this product BA, which we have just defined here. So this is a map of sets. Okay, on the left-hand side, you have a set which is the Cartesian product of two sets, and on the right-hand side, you have a set which is just a space of matrices. Now, on the left, we have more structure. So we can say more about this product, which I will do later. At the moment, I don't want to do it. Okay, so now that we've defined the product, we can now come to the most important fact about matrices, which justifies many things, including the definition of products. And that is that matrices can be identified with linear maps. So this is not a precise mathematical statement, but this is something. Think of this as a sentence in English, which has to be made precise in mathematical terms. So I'm going to justify this now. So consider. Now, see, I'm going to be quite fussy about notation because I'm going to talk about the correspondence between matrices and linear maps. So on the one side, there'll be matrices, and on the other side, there'll be on the one side, there'll be a matrix, and on the other side, there will be a corresponding linear map. So and I'll be going back and forth between these two things. So I need to keep my notation straight. So in short, if you see a capital letter, it's a matrix. And if you see a capital letter with a hat on top, it's a linear map. And you go from matrices to linear maps by adding and removing the hat on top. Okay. So I'm going to now go from linear maps to matrices. So I start with something with a hat. Consider a linear map A hat from the space M n cross 1 to the vector space M cross 1. So these are both spaces of column vectors. Column vectors of size or size n, or sometimes you say length, and these are column vectors of size m. So we know that for any, if I fix the number of rows and number of columns of, then the space of matrices with this size form a vector space. So in particular, column vectors of a given length form a vector space. So Mn cross 1 is a vector space, and M cross 1 is a vector space. So, and I'm considering a linear map A hat. So now I'm going to associate a matrix to it. And to do that, we have to actually choose bases. So this is going to be the lesson going forward. If you want to associate a matrix to a linear map, you have to choose a basis for the vector spaces involved. Now, the point is that the space of column vectors comes with a natural basis. So the choice is made for you. So there is, in fact, a natural way to associate a matrix to a map, linear map between column vectors. So that is what is happening now. So just remember, in the future, we will do this again and again. To study linear maps, we will associate matrices to them. But in the future, we will be not necessarily in a situation where the vector spaces come with a basis. In which case, to associate a matrix to a linear map, you have to make a further choice, namely basis. You have to choose basis before you can go between linear maps and matrices. So in brief, matrices are linear maps plus basis. Now, but now because we are looking at linear maps between column vectors, the basis is given to you for both vector spaces, for column vectors of length n and column vectors of length m. The basis is given to you, and that is what we are going to be using going forward to associate a matrix. I'm just giving you a preview of what's coming in the next few minutes. So now, so having said what I'm going to do, you can almost do it yourself. What is a basis for column vectors? Well, if you take a column vector with all entries 0 except 1, where you have the entry 1, and let this position of this 1 change, go down from top to bottom, you get a basis. So in other words, let ej equal to 1 to n denote the column vector of length n. Ej is the following: 0, 0, 1, dot, 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 0. And this 1 appears in the jth place. So as j runs from 1 to n, you get a basis for which vector space? Are you guys there? No, column vectors, which one? Of length?
N.
Length n. So you get a basis for this vector space. See, there are 2 vector spaces here. So I've chosen a basis. So now I've exhibited a basis for this. Now, similarly, let E prime 1, E prime M be the corresponding basis for M cross 1. So I have E1 EM. This is a basis for M cross 1. And this, with the primes, you get a basis for this. This is N cross 1, sorry. Is everybody with me? So I've taken the column vectors of length M. I've exhibited a basis for it. These are the EIs with the prime. and the basis for column vectors of length n are the EIs without the prime, without the dash on the top right. Was there a question?
Sir, can you repeat what you said before this topic? Like you said,
Yeah.
Sometimes there won't be basis.
Yeah. So there won't be a basis given to you. See, every finite dimensional vector space has a basis, but there will not be a basis that's given to you. Okay. Whereas if I take column vectors, there is a basis that's staring you in the face, namely the one that I exhibited. So when I associate matrix to a linear map from column vectors to column vectors, what we do, see, I could have done all this without talking about this. I'm just said all this because later on, this business about choosing a basis will be important, because we will be interested in doing things about linear maps between vector spaces, and these vector spaces often will not be given from the description. There will be no natural choice of a basis, and often the linear maps themselves will not be presented in terms of a matrix. They will be presented, for example, you could take polynomials of degree d and take the derivative, or so there is no God-given basis. So then to study the derivative as a linear map, and often it's useful to associate a matrix to the derivative, in which case I have to choose a basis for polynomials of degree d.
Okay.
And there are many natural bases. Okay, and so the same linear map will appear as different bases, different matrices, depending on which basis you choose. Okay, so I'm giving you a preview of what is going to happen. But if this is confusing you, just forget about it. At the moment, we are interested in associating a matrix to linear maps between the spaces of column vectors. That's what we are doing now.
Thank you, sir.
Yeah. So now, so we have done this. So we have this linear map. Let me recall. I have a linear map from n cross 1 to m cross 1. And I have to somehow associate a matrix A. And what I have done is, we have done this step. We have chosen basis. I say basis with an E because there are two bases, one here and one here. Okay, these are the E's, EI's, and these are the J primes. So these guys on the right, these are the prime vectors, and on the left I have the non-prime vectors. And now the next step. So what do I? So this will be a first of all, to begin to end your suspense. This is going to be the M cross N matrix. So to every linear map from the space of column vectors of length n to column vectors of length m, we are going to associate M cross N matrix. How are we going to do that? As follows. Define. So A is going to be the matrix A11, M1, sorry, A1N, AM1, AMN, where these guys, the small a's are going to be defined Aij, I equal to 1 to m, j equal to 1 to n, are going to be by, you take your linear map A hat, apply it to the basis. So this is a vector in M n cross 1. And when you apply a hat, I'll get a vector. The result, this whole object is going to be a vector in M cross 1. So that can be expanded in terms of the basis Ej prime. So sigma E I prime E j I equal to 1 to n. Equal to 1 to m. Yeah. So so that is how the AIJs are defined. So this procedure, it should be clear to you. If it's not, I can spend the remaining 10 minutes explaining this, and then we can come back to it in the next lecture.
Sir, could you please repeat, like after choosing the basis, what did we do?
Okay, so look at this red arrow. This red arrow is telling you what I am going to do. I'm starting with a linear map, and I'm going to associate a matrix. And I've told you what the size of the matrix is going to be. It is going to have m rows and n columns. So I have to give you a rule. Start with a linear map, and I have to give you certain real numbers. How many real numbers do I have to give you? I have to give you m times n real numbers, because n cross n matrix has m times n entries, right? So I have to tell you what is the rule that associates to a linear map A hat these real numbers. Are you okay so far?
Yes.
Okay. Now I take the linear map A hat. I can when I apply it to any vector in this vector space, I should get a vector in this vector space, right? Because it's a linear map from here to here.
Yes.
Okay. Yeah. So in particular, if I apply it to any of the basis vectors of this vector space, I should get a vector here. Not necessarily a basis vector, but I will get some vector here. Okay.
Yes.
Now, this vector space has a basis, which are the prime vectors, these guys. So any vector here has a unique expression as a linear combination of these prime vectors. That's what it means for a set of vectors to be a basis.
Yes.
So in particular, so fix a j and hit it with a hat. I get a vector here that will have an expression as a linear combination of the prime vectors with some real numbers sitting in front of them.
Yes.
Okay. And that real number, first of all, has to depend on the vector here. So that is this part. And then for every I running from 1 to n, I'll get a real number. So I get these m real numbers.
Got it.
Okay. Now as j varies, so as j varies, j will run from 1 to n. So I'll have m times n real numbers, and I arrange them into this matrix. Okay.
Yes.
So I have associated to every linear map a matrix. So now, so I get a map from
Sir, one doubt, sir.
Yeah.
The linear. So for some linear map,
not for some linear map. For every linear map, I get a matrix.
Yeah. So for some linear map, you get one type of matrix by solving these equations. Am I right?
No. I don't want to talk like that. I don't even know what you mean.
No, sir. So the M cross N matrix is not given initially, but it is associated with each one of different maps which are possible from M cross 1 to N
linear
cross 1.
map, there is a matrix.
Yeah. So, but it is not initially given. It is generated by the given map. Am I right?
I don't know what you mean by generated. I'm saying I'm for every linear map, I give you a matrix. And I've given you the rule for how to do this. So you have to understand the rule. So the rule is extremely straightforward, but it is given in terms of some abstract concepts. So do you understand the concept?
Yeah. Yes, sir. Thinking, sir.
No. You are right to be hesitant because it is somewhat implicit. So I'm going to just spend the rest of 5 minutes doing this, and then we will come back to this. Okay. You start with a linear map, A hat. Okay.
Yes, sir.
Linear map is from this vector space to this vector space. Okay.
Yes.
Now, so when I act on any vector here, I will get a vector here. So in particular, I have n special vectors here. The vectors belonging to this basis set, E1 to EM. These guys.
Yes, sir.
Okay. This should be n, I think. Sorry. Yeah. So I can apply A hat to each of these n vectors. So now apply to one of them, EJ, I'll get a vector here. Now, this has a basis, namely these guys are a basis. So any vector here can be expanded in terms of this basis. So it will be a unique linear combination of these guys. Oh my God. Okay. So
yes,
in particular, A hat EJ can be written in terms of the EI primes with some real coefficients AIJ. So if for a fixed J, how many AIJs are there? There are M of these. But J itself can run from 1 to n. So there are M times n coefficients that I get. So I associate every A hat, this M times n real numbers, but you should really think of them as being arranged in this array because there is a particular indexing that comes from my rule. So I'm not solving any equation. I'm associating to a linear map an array of real numbers. And I've told you how I'm doing this.
So is it like this? Given an array, given a 2D matrix.
That would be going in the other direction. I'm going from the linear map to the array. We will go in the other direction later.
Oh, okay, sir.
At the moment, I go from a linear map to the array. We will go in the other direction also later.
So I have a slight problem. What you're doing is you're assigning a set of points to every basis in the domain.
Set of real numbers.
Yes, so a set of real numbers for every basis. And they're claiming
and the
that
basis itself runs over the.
Yes, for every basis.
There are n basis vectors. So for each of them, I'll have each basis vector on the left. I'll have n real numbers, but the basis vectors on the left, there are m of them. So I'll have m times n real numbers.
So you're claiming that this creates a map, a linear map. I mean, it does make sense, but so like
no, I've just at the moment I've just given you an association of a matrix to every linear map. We will study properties of this later.
So I mean, for any linear map, I mean, if we don't consider.
No, for any linear map, I have associated a matrix.
Okay.
Yeah.
So the question was, if we suppose we have any linear map, I mean, not considering the matrices.
No. I mean, wait. At the moment, this is only for a linear map from one column vector space to another column vector space. Column vectors of length n to column vectors of length m.
Okay.
So this is in this specific context, column vectors of length n to column vectors of length m to any linear map. So the vector space m n cross n to m m cross m, any linear map, I have associated a matrix. I'm not considering arbitrary vector spaces. I'm considering two specific vector spaces, column vectors of length n, column vectors of length m. Fix these. Now, for every linear map from column vectors of length n to column vectors of length m, I have associated an array of an m cross n array of real numbers. That is all that we have done so far.
So what's the intuition behind defining?
No intuition. I am not in the business of selling intuition. Sorry. Intuition will come later with exercises and thinking, etc. I cannot give you intuition. Okay, so as I said, I will. My notes on matrices are quite carefully written. You have to study them, think about it, and we will come back and do it slowly. I'm sorry about intuition. I have no intuition to give you. Intuition will come with looking at the definition, looking at examples, looking at exercises. I cannot give you intuition. Okay, so but we are only halfway there. As I said, I mean, now I need to stop and give you the short quiz. It's extremely short, extremely simple, and I'm going to first of all yeah, there was a question about square matrices earlier. I will deal with this later. Yeah, I might have. Yeah. Okay, let us start.